Welcome everyone to today's seminar. Piotr Kawalek is live here in Boulder, and we'll talk about complexity of satisfiability and equivalence problems in finite algebras. Please.
Thank you, Peter. So, when I will talk about complexity, I will especially concentrate on algorithmic complexity. So, we want to analyze how certain satisfiability problems for equations, how complex algorithms we need to solve certain equations coming from algebraic structures. So let's look at some easy examples. So when we have systems of linear equations in rational numbers, then of course we have Gaussian elimination algorithm that we can use to check if a given system of equations has a solution or not. And of course this algorithm is quite fast. So the number of equations increases, then the time complexity or the number of arithmetic operations we have to use to solve this system grows like a cubic function. So
excuse me, am I the only one who's hearing that echo? I cannot understand a word, I must say.
The sound quality is very bad.
Sorry?
The sound quality is very bad.
Yes.
It's very bad.
Okay.
I can practically not understand anything.
Yes,
that's true. It's a lot of echo.
I also understand very badly.
So try to fix it.
We're trying. Is that any better now?
Yes,
Perhaps,
for me.
perhaps.
I think whoever's speaking has to be very
Say something
closer to the
again.
microphone.
Yeah, I think so.
Is the sound better now?
Yeah, it's better, but maybe it has to do because you're close to the micro.
Okay, so maybe I'll sit near the computer. Is it better?
Yes, better.
Okay.
Yeah.
So I guess I'll sit near the computer then.
Yeah.
To be heard.
Yes, it's better.
It's excellent now.
Yeah.
Excellent.
Okay, so maybe once more I will be talking about algorithmic complexity of solving equations in different algebraic structures. So we all know the Gaussian elimination algorithm that can be used to solve systems of linear equations, and this is quite fast algorithm, which means that if the number of equations grows, then the number of arithmetic operations we have to perform in order to check satisfiability of the system of equations grows like a cubic function. In particular, it's a polynomial function. So if the complexity of the problem with bigger and bigger inputs grows as like a polynomial function, then of course, in computational complexity, we consider it as a fast algorithm. On the other hand, some types of equations can require more time. So for instance, even if we restrict attention only to finite fields, and we get one equation over finite field, then the problem of solving equations in finite fields becomes NP-complete. So we have some brute force search algorithm, which takes exponential time, but unless P is equal NP, we cannot do much better. Yeah, so we will be like looking at different algebraic structures and different problems of solving equations, and we will try to find out when the problem has polynomial time algorithm and when the problem is NP-complete. And of course, there are in the class NP of computational problems, there are also NP intermediate problems, so they are maybe a little bit harder than problems in the class P, but maybe a little bit easier than NP-complete problems that are the hardest ones in the entire class of complexities. Yeah, so of course, if we want to prove that problem is NP complete, we need to take some problem that was previously known to be NP complete and make a reduction to our problem, and this reduction must be polynomial time. Usually is polynomial time reduction. And in this presentation, I will only use two NP complete problems. So Q coloring is a problem in which we get a graph and we want to color its vertices with Q colors, and we want coloring to satisfy the condition that each edge has two different colors at the ends. So such K coloring problem is famously known to be NP complete for K at least 3. And of course, 3SAT, we get a formula in conjunctive normal form, where we have conjunctions of some length-free clauses, and we want to satisfy it. And it's also an NP complete problem. Okay, so maybe let's look for warm up how to prove NP completeness for fields, for finite field FQ. So when we have finite field, we will encode Q coloring problem in the problem of solving equations in the field. So if on the input we get graph of on n vertices and some list of edges, then for each vertex we create variable ci, and we subtract variables corresponding to the same edge. We raise it to q minus 1, and we multiply this subtractions. And well, we get some simple equation. We want this multiplication to be equal 1. And we can easily see that this equation is satisfied if and only if the initial graph had a legal Q coloring. So if the graph had legal Q coloring, we can just use the numbers corresponding to colors and substitute them for variables. And of course, things will multiply to 1 by Fermat's theorem. And of course, if this multiplication is 1, then all the subtractions must be must be non-zero. So CE must be different than CJ. So we get a legal coloring. So we could solve Q coloring using algorithm to solve equations in the finite field. So this is an easy proof of NP completeness. Okay, but in general, it can be even worse. Of course, we know that Diophantine equation have no algorithm. So if we want to solve in the ring of integers equations, then the problem is famously known to be undecidable by Matiasiewicz result. So yeah, we have many different complexities that equation solvability, in particular algebraic structures, can take. So in this talk, we will concentrate on this part where at least we have this brute force search algorithm. So we are at least in NP. So the easiest way to guarantee we are in NP is to restrict domain to be finite. So we have a finite domain and some operations over this domain. And these operations are the only operations allowed to appear in the equation. So we have two problems: solving systems of equations called sys-POLSAT, and problem of solving one equation called POLSAT. And in the first problem, we get pairs of polynomials of the algebra, and we want to find an assignment that makes this polynomials pairwise equal. And in the second problem, we get only one equation, and we want to find out if there is satisfying assignment to variables. Yes, so the goal would be to describe for which algebraic structures we have polynomial time algorithm and for which the problem is NP complete. So I cheated a little bit. The problem of solving systems of equations is already solved because it for any particular algebraic structures we can find a CSP instance which is equivalent to it, and CSPs were classified by Zhuk and Pulatov not that far ago, so we can translate this classification for CSPs back to systems of polynomial equations. So for problem of systems of polynomial equations, it turns out that we only have cases where the problem is tractable in polynomial time, or problem immediately becomes NP complete. So there are no like any intermediate complexities here. We have such a nice dichotomy result. However, for one equation, situation is not clear. So some algebras that induce hard problems of solving systems of equations can now induce easy problems with one equation. And we would be interested to find maybe similar dichotomy, or find out if maybe we can find some intermediate problems here. So yeah, systems of equations is solved. So let's find another problem to think about. So we will also consider checking if the identity holds. So problem of polynomial equivalence. So we get two polynomials of the algebra, and we want to find out if these polynomials compute the same function. So for all assignments, they take the same value. So maybe some comments initially before I present some results. So usually Polsat and Polek have the same complexities. It's kind of hard to find algebras for which we have one problem hard and the other problem easy. So maybe like distributive lattices are an example of such phenomena. So for distributive lattices, we have some very fast algorithm for Polsat, while polynomial equivalence is co-NP complete, so we don't expect fast algorithm here. No, maybe only for trivial lattice like Polek is tractable, of course. But for groups, before I started looking at this topic, there were no examples for which Polsat and Polek were different. So it may be interesting to also look if we can find such examples. So let's focus in the first part of the talk on groups. So for groups, we have multiplication inverse, and we get some equations in this signature. So there was an initial paper of Goldman and Russell on the topic, and they showed that if a group G is nilpotent, then solving one equation is in P. And if the group G is non-solvable, then solving Polsat is already NP complete. So we have this nice cream area in the middle where we don't know the complexities, and we want to find out what is the situation. And of course, nilpotency and solvability just take the standard notion from group theory. So yeah, there was series of papers about the problem, which maybe we can summarize with one result that is more general than all the others. So if we have a semi-direct product of a P group and a abelian group, then the problem is in P. So maybe someone could think, well, this cream area then must be entirely green, right? Because we have some new class of groups for which we have polynomial time algorithm. And maybe in the screen area, we can look at examples which were unsolved 5 years ago. So among them were like dihedral groups, for instance, or the group S4 was the smallest known example for which we didn't know the complexities. So let's look. First on dihedral groups. So we have group of symmetries of regular M-gons. And already here we have kind of surprising results. So for dihedral groups, we have probabilistic polynomial time algorithm. if and only if M has at most one odd prime divisor, assuming RETH. So there is like a lot of things here. So first of all, this proof is under assumption of the lower bound. So the proof that for M that has at least two prime divisors, we don't have polynomial time algorithm, assumes exponential time hypothesis. So it is just a stronger version of P non-equal NP. So this hypothesis assumes that we have a really strongly exponential time lower bound for free-sat problem. So we really need exponential number of steps, not some smaller number of steps to solve free-sat. And currently best algorithm for free-sat is 1.3 to the n. So many computer scientists believe that it's really, this hypothesis really holds, and it's especially useful to determine precise complexities of certain problems. We can really figure out some complexities very precisely if we assume ETH. So here we use ETH to prove upper bounds. So RETH is just randomized version that there is no probabilistic algorithm faster than 2 to the n. And yeah, in the remaining cases, we have probabilistic algorithm. So maybe let's look what type of probabilistic algorithm. So this is, we have algorithm in RP. So maybe a little bit of definition for this, those who don't know this complexity classes. So we say that the language or decision problem is in RP if we have algorithm that runs in polynomial time and takes the input as well as some random input. So we have additional input that will make the algorithm act non-deterministically. So it will just do some random actions based on this random input of length polynomial in the input length. And of course, we require algorithm to still run in polynomial time. And if some element should be accepted, so it belongs to the language. So for instance, if the equation on the input is satisfiable, we want to find out it's satisfiable with large probability. So maybe sometimes we will be wrong, but in most cases, our random bits will let us find this solution and answer yes. So we require probability of failure to be constant. And if our equation is not satisfiable, or if we are supposed to reject the input, then we always reject because, well, we didn't find a solution, so we reject. So it is widely believed that P is equal RP, or more generally, P is equal BPP. So every probabilistic algorithm can be de-randomized. But yeah, sometimes it's much easier to find randomized algorithms. So yeah, we have randomized algorithms for these dihedral groups with one odd prime divisor, and yeah, currently we cannot randomize it. So it's maybe interesting problem to look at. Yeah, how do we prove lower bounds? Well, usually you prove a reduction from free-sat to your favorite problem that you want to show hardness. And here, the difference is that we do sub-exponential time reduction. So we try to encode free-sat instance in size roughly 2 to F root of n. And it is possible in these dihedral groups with at least 2 prime divisors, where R is the number of divisors, of course. So if we could solve equations in these dihedral groups, we could just take any free-sat instance, encode this as an equation in dihedral groups, and then solve the equation. And this way we would solve free-sat instance in sub-exponential time, which is contrary to ETH. This is kind of the idea. And this algorithm which works is very, very simple, actually. So if M has one odd prime divisor, we just assign random values to variables. And basically, if there is a solution, we are likely to find it with large probability. So if the equation has length L, if we just try polynomially many different assignments to variables, polynomially many candidate solutions, we are very likely to find one. So we have constant probability of failure. And we can generalize, of course, this kind of result for dihedral groups to larger class of groups. So if G has a normal P subgroup with quotient G/GP being nilpotent, then we know that PALS has also this naive probabilistic algorithm. And there is another complexity assumption here. I will for now leave it. But if G modulo GP is abelian, then we don't need this PDH. So this is another computational complexity assumption. Okay, so dihedral groups, like maybe let's reflect a little bit on the structure. So dihedral groups have this homomorphic image into Z2, because of course reflections act like Z2, and we have this normal subgroup of rotations beneath it, and this we can like in a sense see that Z2 is acting on this group of rotations. And let's look at the other group, S4. So in S4, we also have homomorphic image to Z2. We have normal subgroup isomorphic to Z2 times Z2. Somewhere in the middle, we can find something which looks like Z3. And yeah, for this S4, which was also open, we also can prove with sub-exponential reduction from free sub a super polynomial lower bound. So we do not have polynomial time algorithm for S4, assuming ETH. And well, the algebraic reason is maybe that this diagram has height 3. And of course, we need to be smart how to generalize it. So we need to define this height properly. So it turns out that the good definition is just take a look at the lattice of normal subgroups of G, and if we can divide this lattice of normal subgroups into like H slices. So if we can go from one element from this unit normal subgroup to the entire group, and in each step we take larger and larger groups, and if GE/GE-1 is nilpotent, then the minimal number of steps we need to take in this process is called the nilpotent rank of a group, and it of course makes sense only for solvable groups. So if we have this nilpotent rank to be at least 3, then the PALS problem has no polynomial time algorithm, and we can make some kind of construction showing that there is no polynomial time algorithm. And this kind of thing can be generalized to Maltsev algebras. So we can do it even more generally for PALSAT. But we need to like generalize nilpotency in a standard way to algebras. So we are left with groups of nilpotent rank 2. So they have nilpotent normal subgroup such that the quotient is also nilpotent. So this is kind of a diagram that has more colors now. So we showed some new examples of groups that have polynomial time algorithms. And recall this algorithm is just taking random assignments. And if this algorithm doesn't work, we have some lower bounds, which is orange color, because this is not NP-complete class of problems. This is just some class which is not polynomial time solvable, assuming ETH. So there are some circuit complexity assumptions that can help us to show that these problems are in fact NP intermediate. So yeah, so maybe for solving one equation, it is really not that clear what is the situation. Maybe there are really some NP intermediate problems, and these orange problems here are good candidates. Of course, it's very hard to prove unconditionally such things, because then we would probably understand computational circuit complexity enough to prove P is non-equivalent P. So, and unlikely. And yeah, we can of course extend these results even more, so we can prove polynomial time algorithms for more groups. So we can like consider groups that generalize dihedral groups, and we can draw kind of similar diagrams. So this kind of diagram also gives us this randomized algorithm, even if we add another like coordinates, let's say. So for instance, if we take a real product of ZPQ and ZPQ, we still can prove there is a polynomial time algorithm, and it is kind of application of the reasoning for the substructures, let's say, of these big groups. So we can extend this naive randomized algorithm, and in groups it is in fact the only thing that appears to happen. So the only reason for polynomial time algorithm is just taking random assignments, weirdly. Yeah, this is maybe some generalization of this fact that if we have semi-direct product of two nilpotent groups and G has two prime divisors, then we also can show probabilistic polynomial time algorithm. However, Polsat problem is quite complicated. We have some kind of weird examples of groups where we still can't figure out the complexity, so it looks kind of difficult to figure out the exact complexities here. However, if we modify the problem a little bit, so if we consider the problem with lists, so this is variant of the problem list Polsat. So together with equation, we want like more specific solutions. So we want our variables to satisfy also some condition. We specify some values that we want to variable to take. So for each variable, we have some lists of allowed values. And in this variant of the problem, of course, we have some groups can become harder to solve. So this problem, well, already admits a nice diagram. So we can actually show lower bounds for all groups that are not this easy examples where we have normal GP subgroup and nilpotent quotient. So we can fill this diagram with hardness proofs. On the other hand, yeah, I mentioned at the beginning this Polek problem. So for Polek, we have even nicer description. So for Polek, we have a polynomial time algorithm when the nilpotent rank is equal to. So this is kind of very nice description. Okay, but what about Polsat? So maybe the reason why Polsat is so hard to figure out is that, well, the problem doesn't have a nice algebraic properties. So for instance, if you take alternating group A4, then the problem is in P. However, if we allow in the equations also commutator operation, then the problems becomes NP complete. And well, it's a little bit weird because commutator is of course expressible with multiplication and inverse. But the reason behind this weird phenomena is that, of course, with commutator, we can encode certain polynomials by a shorter term. So we kind of can make like some kind of encoding easier with commutator. But it is not nice because for the problem, because well, the problem doesn't depend on the clone of polynomial operations. We have some weird signature dependence. But there is a solution proposed by Paweł Idziak and Jacek Krzaczkowski, so maybe we should encode the equation in a different way. So the idea is to use circuits instead of polynomials. So for instance, if we have x1 plus x2 square and its corresponding expression, then with polynomials we have to define x1 plus x2 twice. And it seems redundant, so we just allow to reuse sub-expressions that were once defined. So we can draw a circuit. So from one node we can get two edges going outside, and we can reuse the computation we made once. And it leads us to the problem CSAT. So it's very similar problem, but we get these polynomials on the input as circuits. So what happens now? Well, it turns out that for many algebraic structures, now the picture simplifies. So for groups, if the group is nilpotent, we have a polynomial time algorithm. And if the group is not nilpotent, suddenly CSAT is NP-complete. The same for rings, only nilpotent rings have polynomial time algorithms. And lattices, while distributive lattices have polynomial time algorithms also. So, well, this problem has nicer properties. Maybe we can consider more general algebraic structures. So far, I think the problem was mostly considered for by either in monoids or in some variants, or we considered it in congruence modular variety. So there is the initial result of Idziak and Krzaczkowski that kind of inspired my research. And they show that if either algebra decomposes as a direct product of nilpotent algebra and something which has similar properties to distributive lattice, then maybe there is hope for polynomial time algorithm. But if A has no such structure, then we have some congruence such that the corresponding quotient leads to NP-complete CSAT. So maybe it's a little bit technical, right? Because we have this congruence, but yeah, we believe that you can get rid of this congruence, and we did it in many cases. Well, for this DL-like component, in the second dot, there is polynomial time algorithm. So we, in fact, have to understand nilpotent algebras here. But nilpotent algebras are kind of different than nilpotent groups. So nilpotent groups decompose into a direct product of algebras of prime power size by Sylow theorems, and nilpotent algebras don't have such nice properties, at least with a standard universal algebraic notion of nilpotence. But, well, there is another notion which is maybe not that old as nilpotence, which is super nilpotence. And for super nilpotent algebras, already Idziak and Krzaczkowski and simultaneously Kompaczer showed that there is a polynomial time algorithm for solving CSAT. So what are the super nilpotent algebras? So we can define them with certain term condition, but what is important for us is that super nilpotence for finite algebras is stronger than nilpotence. And well, prime power size nilpotent algebras are super nilpotent, and their products is also super nilpotent, and nothing else in CM is. So kind of have this nice structural result, which makes super nilpotence in CM similar to groups, to nilpotent groups. Well, and maybe I'll kind of show you some reasoning. How roughly do you show a nice algorithms for super nilpotent algebras? So if you have super nilpotent algebra of size P to the K, then one can show with a smart analysis of the Riff product decomposition of this nilpotent algebra is that we have an isomorphism from the domain to algebra to some power of ZP. And this isomorphism has also nice properties. It has nice interaction with polynomials of our algebra. So if we take another polynomial of our algebra and any constant C in the algebra domain, then we can find bounded degree polynomial QC over the field GFP, which kind of simulates our polynomial from algebra. So whenever polynomial in algebra takes value C, we can translate with this isomorphism variables. We can split variables to K variables and feed them to this bounded degree polynomial. We can kind of translate equation in super nilpotent algebra to the equation over this bounded degree polynomial. And the degree is maybe large because it's roughly A to log M, where M is arity of maximal operation. But well, it's still bounded degree, and we can use it. So how to use it? When we have nilpotent algebra, we have a nicely behaving Maltsev term. So if we get equation, we can translate it to an equation with a constant on one side with the Maltsev term, which has like some nice permutational properties. And thus, then we can use this when we are super nilpotent and of prime power size, we can translate this equation to this polynomial equation in the finite field of bounded degree. But well, equations over of bounded degree in finite fields have a very nice property that, well, if we take random assignment again to them, then we have constant probability to satisfy them. So this is like really strong because we have constant probability of satisfying them. So as this translation uses some bijection, then we can translate this back to the super nilpotent algebra. So we can see that the initial equation, if we take just random assignments to variables, then we get a solution with like large probability if this solution exists. And this leads to actually not only polynomial time algorithm, but actually probabilistic linear time algorithm. So these are real results of Ijak-Krzoczkowski and Kompacz were deterministic, so there were no algorithm, no random bits there. But this algorithm is much faster. So they have like some very big constant in the complexity of their algorithm in these older papers. And here we have linear time algorithm. And that actually allows to show like very nice, very strong dichotomy for groups. So if we have finite groups, then CSAT is either solvable in probabilistic linear time or is already NP complete. So we have like big gap of complexities kind of here. Okay, what else? We have the super nilpotent algebras. What about general nilpotent ones? So the simplest example from which we started like investigating examples before generalizing was the Z6 group with additional mod 2 operator. So we have additional unary function which kind of prevents us from decomposing it into an Riff product. And for this type of algebra, we can make something similar actually to super nilpotent algebras. So for super nilpotent algebras, we kind of translated them to bounded degree polynomial. And it is like combinatorial object that corresponds to them in this setting. And for this Z6 with addition, the combinatorial kind of analog are so-called mod3, mod2 circuits. So what are those circuits? So these are circuits computing Boolean functions. So we have 0 ones on the input and zeros and ones on the output level. And gates are just computing some addition moduli. So in the middle layer, we have only mod p gates, and this mod p gates just sum the inputs, and if the sum is in some accepting set R, we output 1, otherwise we output 0, and proceed with the computation. So we have different accepting sets for different gates. Maybe this allows us to compute a little bit more. So such a circuit is called mod P, mod Q circuit. So we kind of have similar idea. So we have this equation over this Z6. We translate it to equation over this mod 2 mod 3 circuit. And well, by some old circuit complexity results by Barrington, Straubing, and Ferrier, and some new observations that we made recently, this circuit equation has like our favorite property that it either has no solution. This equation over circuits either has no solution or it has a lot of solutions. So again, taking random assignment that gives us good enough probability of finding a satisfying assignment. And well, maybe it's not clear in this case, but it also translates back to the initial equation. So even though this circuit is Boolean and algebra is non-Boolean, we can still make this kind of reasoning. And well, the circuit translations are possible for all nilpotent algebras, apparently. So if you are very careful with translating your algebra to circuit, then you can capture the complexity kind of through circuit complexity notions. So this, when you like generalize this reasoning on Z6, you can push it to something like this. So if we have some super nilpotent congruence alpha such that M modulo alpha is abelian and alpha has prime power size classes, then CSAT for this algebra is in RP. And if we again use this assumption of CDH, we can even extend it. So there is this circuit complexity assumption to the case where A modulo alpha is also super nilpotent. Well, what is the CDH maybe? Now it will be clearer why it connects. So CDH says that if we have a circuit which is and the mod P, there is a mistake. There should be and the mod M mod P circuit. So if we have and the mod M mod P circuit, then we require really exponential size to compute and N. And this D is fixed here. So we have additional layer of bounded arity AND gates, and we want to express unbounded arity AND gate. So the reason why this result uses the assumption of CDH is that these algebras, if we look at combinatorial object corresponding to them, we exactly get this circuit. So we kind of can see that we can use some assumption about the circuit to prove some algorithms working. Okay, so this is kind of the most general algorithmic result so far. What about lower bounds? So for groups, there was this notion of nilpotent rank. It turns out that for algebras, we can kind of modify it. So here, we would like to slice the congruence lattice into super nilpotent intervals. So we can also generalize the super nilpotence to congruences, and we can kind of split the congruence lattice into super nilpotent intervals. And the smallest steps we need in this splitting is super nilpotent rank. And if the super nilpotent rank is at least 3, then we all again can show super polynomial time algorithms for some algebras, and Piotr generalized this to all algebras. So we have kind of similar thing. And yeah, maybe the strongest application we have so far is that we can basically fully recognize polynomial time cases for circuit equivalence. So, well, we have that circuit equivalence is in RP for algebra A in congruence modular variety if and only if the super nilpotent rank is equal to 2. So we have this assumption of CDH and ETH here, of course, which we would love to get rid of, especially CDH. Maybe someone can prove CDH, but we also can show that proving this classification without assuming CDH is equivalent to proving CDH. So this CDH is really here. So roughly speaking, how it goes by some old Ijak-Szotkowski results and our newer results, we can assume A is nilpotent. Using this composer result, we can reduce to super nilpotent rank 2 case, and then we need to use some properties of super nilpotent congruences by Peters and Agner's paper, plus do some smart translation to the circuits, use some semi-direct product decomposition of our algebra, and we arrive at this quite nice result. So maybe to slowly finish, so we saw some results for groups and for algebras from CM, and maybe one can think that they are pretty similar because, well, let's look at this. We have algorithms where A has a congruence alpha such that A/alpha is super nilpotent, and alpha has some classes of prime power size. And for groups, we had like algorithm where we had a normal P subgroup such that G/dp was nilpotent. So it looks kind of similar. The algebraic notions used here are different, and of course CSAT is a different problem than POLSAT, but it looks kind of similar, right? So the reason is that, well, if we do these translations to combinatorial object, circuits over nilpotent algebras translate to CCHM circuits, and we can do similar translations for polynomials over solvable groups, and we also will end up with similar translation at CCHM circuits. So despite that, like the algebraic notions are different, and the circuits and polynomials like are different kind of objects, if we do this combinatorial translation to circuits, we will see at the end the same kind of circuits. So this combinatorial structure of the problem is kind of similar at the end. Okay, so we have a bunch of unresolved problems, both for POLSAT and CSAT. So there is still plenty of things to do in this area, but I hope I kind of showed you some basics here. Thank you.